guess it's time is 11:40, so let's get started. I guess I'll start with good morning, everyone. Welcome to NDC Portal, and welcome to this talk on how to build a social network on serverless. So my name is Yan Cui. I'm a principal engineer at a company called The Zone. We do sports streaming. At the same time, I'm also one of the AWS serverless heroes. So for those of you who are not familiar with what that actually means, it's essentially Amazon's equivalent to Microsoft's MVP program. And I'm also doing some independent consulting work on the side as well, since I've been working part-time at The Zone, which, as I mentioned, is in the sports streaming business. We call ourselves Netflix for sports, partly because we have a very similar business model in that we offer a subscription-based platform that allows you to watch any sports that we have on our platform. But also kind of because we kind of stolen the Netflix's UI, as you can probably tell from the screenshot I'm showing you here. And we have offices in London, Amsterdam, Leeds, and Katowice, and we have over 40 different sports and over 300 different leagues all around the world. In the last 6 months alone, we have launched in Italy, including streaming Serie A and Serie B, and in the first weekend, we accounted for something like 50% of the internet traffic in Italy when we first launched there. Since then, we've also launched in the US with boxing, and as we speak, we launched in Spain yesterday. So that makes it 8 countries and over 30 different platforms and devices. At peak, we have around 1 million concurrent viewers on our platform, which, as you can imagine, has some interesting technical challenges, which right now we are tackling those challenges using both serverless, but also containers as well. So as a company, we very much are serverless first, but there's many cases where serverless is still not a good fit for every single use case, so we are using containers as part of architecture as well. But as you can see from the title of my talk, I'm not here to talk about sports streaming. That will be a different talk at a different time. What I want to talk about today is some of the work that I did in one of my previous companies where I was building a social network that you can think of as a mix of Instagram, Twitter, and Facebook. And it was really there that I learned an awful lot about AWS Lambda and what it takes to run a serverless architecture in production. So when I joined Yubble, the social network, we had a pretty monolithic system that is very simple on paper, but under the hood, we had lots of complexity and problems hidden inside each one of those boxes. And about 6 months later, after we decided to go fully serverless, we ended up with architecture that is both event-driven as well as service-oriented, and Lambda is a centerpiece that glues everything together. At this point, you might be tempted to ask, just why? Why did you feel the need to take on such undertaking? What is the benefit? So I want to take you back a bit further. So Yubble being an early stage social network, we don't have that many users, so our baseline traffic is fairly low, but we did manage to attract a few influencers from other platforms like Instagram. And these influencers had a big influence on our traffic pattern. So whenever they would run, say, a social media campaign, and people like Emily, who was one of our top users at a time when the whole platform had about 800,000 or million users, she had about 400,000 followers already. When she often would write a post and say, "Hey guys, please vote on this, and I'm going to announce a lucky winner for this beautiful designer handbag at 10 p.m. tonight." So as you can imagine, all throughout the day, traffic is nice and stable and very low, and just about 10 o'clock, you have a massive spike in traffic as everybody who follows Emily comes back to see whether or not they were able to win her prize. So we get all these unpredictable spikes in traffic throughout the day, which has some serious implications in terms of how do we do capacity planning and scaling our applications. We ended up having a much larger cluster than we would like, running at very low utilization so that we have a lot of room to handle these spikes. And because scaling takes a few minutes before a server is actually ready to serve requests, so we tend to scale up a lot earlier than we'd like as well. When you put the two things together, it means that we are spending a lot of money and resources that we're not even using. By my estimate, we will probably, on average, throughout the whole day, using about 5% of what we pay for. And that is bad. And beyond all that, an even bigger problem was that At the time, deployment was taking 30 minutes and required downtime. The whole system had to go down and then back up with nothing in between, so that if you're coming to the app during the deployment, all you see is a buffer phase. There's no even message that says, sorry guys, we are deploying. And that feature often took months to implement. Something simple was taking a very, very long time, and many people to actually develop. And one of my favorite speakers, Dan North, once said that the lead time to someone saying thank you is the only reputational metric that matters. And it's a message that has really resonated with me, has stuck with me ever since. And as engineers, to get that thank you, we need to first provide some value to people. And to do that, we need to ship our software. Until our software is actually shipped and running in production, as far as our users are concerned, we haven't done anything yet. So in terms of our motivation to take this drastic overhaul of our architecture and our approach was first and foremost to be able to deliver a better product, one that our users will actually love to use. And as a team, we want to be able to deliver value to our business quicker, faster. And as a company, we also want to cut down our AWS cost to be more cost efficient. Just to be clear here, I'm not saying that the goal is not to spend less per se, but to spend better. If it's something that's expensive but delivers a lot of value, that's fine by me. But I'm not happy with carrying all this wastage. It's about return on investment. If I'm spending money and not getting any return, that's bad. And once the why is clear to us, we need to decide on the how. We need to figure out what the good architecture would look like for us. And having sat down with the team, we decided that we want deployments to be small, to be fast, to have no downtime. And we also don't want to be in a situation where we have to do lockstep deployment with the client applications because of the sheer amount of coordination and stress that's involved. We also want features to be independently deployable. We want them to be loosely coupled so that every component can evolve at their own pace. And we don't want everything to have to evolve at the pace of the slowest component. And as a team, we also want to minimize the amount of fat that we have in our AWS build, and there was plenty of it. And we want to minimize the amount of time that we spend just babysitting our infrastructure. As far as I'm concerned, the infrastructure should work for me. And if I have to spend all of my time just keeping an eye on the infrastructure, that's not how it's working. I'm looking after the infrastructure. I'm working for the infrastructure. And we also want to reduce the amount of technical mess that we inherited as a team. And that's a very conscious choice of wording. Often you hear people talk about technical debt, but a debt implies a decision to make some trade-off so that future work is required, but you get to ship earlier. And what I found when I took over the architecture wasn't that. And whilst we fixed all this mess that we inherited, we also want to be able to deliver things faster as well. It's not acceptable for the team to take months to deliver simple features. So in terms of the approach we decided to go on, we wanted to build an event-driven microservices architecture. And since we're not an infrastructure company, so the time we spend on managing our infrastructure is time that we take away from us doing the stuff that will actually benefit our users. So as a company, as a team, we also decided to go serverless first. And this talk is about the what. What do we actually do to get there? You may also recognize this as a golden circle, which Simon Sinek talks about an awful lot. If you haven't read his book yet, I highly recommend it. It's amazing. So by the time the whole transformation finished, we have somewhere around 200 Lambda functions running in production. And even though cost wasn't our main driver for this whole migration, we did find that we made a significant amount of cost saving. We were spending about 5% on Lambda compared to what we spent on EC2 for comparable amount of compute, because we were able to cut out all the waste that we had around our EC2 cost usage. But more importantly for me, we went from doing maybe 4 to 6 deployments to production a month to easily doing 100 a month within a few months. And we had the same size team. We just made everybody more productive. We took away all the shackles that stopped them from being able to iterate quickly, and we gave them their superpower back. And oftentimes, features would take days instead of months, and sometimes they were discussed, they were implemented, and deployed to production in the same day. So for the moment, we decided that Lambda or serverless is a good fit for the direction that we want to move towards, to actually having something running in production. We need to be responsible. We need to understand how we're actually going to operate this serverless architecture. And that means we need to answer questions around how do we do continuous delivery? What about testing and logging and monitoring and alerting and so on? And as the architecture expanded to include more services and more functions, many of which have interdependencies as well, we also needed to answer questions around how do we do distributed tracing, what about config management and security. All of that is super interesting to me. I spent a lot of time looking at tackling those problems for serverless, but they're not what I'm here to talk about today. I covered that in previous talks on NDC, and also have a video course with Manning that covers specifically how to tackle those challenges with serverless. And instead today, I want to talk about how we use serverless to essentially rebuild our entire architecture. And one of the first and perhaps most important thing we did was to update our monolith so that you record all state changes as events and publish them into a Kinesis stream. Now, this event-driven approach allows you to have great composability and build systems in a really loosely coupled way. And you can use Lambda or any kind of functional service offering as the glue or connectivity tissue that compose different services together to deliver some business value to our users. In this case, Kinesis is my sink, where different services, many of which are REST APIs that are implemented with API Gateway and Lambda. And when the state changes that's happening in those systems, they can then publish them as events into my Kinesis streams, where other systems, other different boundary contexts, they are interested in very different events. They can subscribe to the stream and react to those events through Lambda functions. And each one of those guys would do their own thing. Some will probably keep a copy of the data they care about in their own database. Others might send out real-time updates through to the clients using WebSockets, using maybe Amazon IoT, and so on. And those other services that are reacting to events, they can also have state changes internally, and they can also publish those events back into the stream to tell everyone else that, hey, I've just done a thing. So that other services that are interested in those events can then react to those and do their own thing as well. So using events, you can build systems in a very, very loosely coupled way. So you go through the process of dividing your system into bounded contexts and microservices. And then instead of having one service having to tell everybody else when some state changes happened, which creates, of course, a lot of coupling between different services. And inside a large company, this often translates into inter-team dependencies as well, which I can tell you right now is easily the top thing that's going to kill a project dead in the water. So instead, with events, everyone just look after what happens inside their own bounded context and publish their state changes to the stream. And they can listen to the stream for state changes happening elsewhere in the system. Of course, this idea is not new to serverless. It's been around for quite a long time. Databases had this same idea with transaction logs. And you also find in distributed systems this similar idea called the unified log processing that's been around for quite some time as well. Now, I love building event-driven systems, and it's definitely my preferred way of building things. But it's by no means a silver bullet. It solves some problems, but it also comes with its own baggage and complexities. And I definitely think that there are many cases where this kind of event-driven architecture is a really bad fit for some problems. So you have all these different subsystems all publishing events into a shared stream, and there's consuming events from that stream. And the common challenge you find is, how do you make sure that when you update your contract, the contract for your events, you don't accidentally end up breaking some other system somewhere else who is depending on your events? I mean, personally, up to now, I have mostly just relied on having discipline and never introduced any breaking changes. But as you can imagine, it's a fairly brittle approach, and it's very hard to maintain as the team grows. It's still pretty early days, but I really like what the async API spec is trying to do, try to give you a way to define your specification for the events and be able to control, to manage breaking any kind of changes to your contract. Another problem or mistake I often find is when you try to implement a workflow inside a particular boundary context using events. In this case, you're making debugging much more difficult for yourself. There's a lot of unnecessary complexity involved with logging, tracing, and more importantly, end-to-end reporting becomes very difficult because the workflow itself doesn't actually exist as a standalone concept in your architecture. is the abstract sum of the different parts, the different event processing logic you have, and it only comes together as a whole inside the mental model that you hold in your head. So I think a better way to do this is use a workflow engine such as step functions or Azure Logic app, where you can capture the workflow itself explicitly. And it also gives you more control around the retries, error handling, and branching logic, and so on. The trade-off, at least with step functions, is that cost is quite expensive service. 1 million state transitions, in this case, will cost you about $25, which is probably 50 times what you will pay for the Lambda invocations themselves. So even as you transition to using a workflow engine, whenever you make state changes as part of your workflow, also don't forget to publish them as events as well, so that elsewhere, some other subsystems in your, some other microservices might be interested and be able to react to those state changes that has happened as part of your workflow. And probably the biggest question I get from people that's trying to adopt serverless is, well, we're still doing microservices by the sound of it, and we're doing this whole large event-driven architecture. How do we actually then organize our functions into repositories? Do we put everything, all my functions, inside a single repository? There's definitely pros and cons to this mono-repo approach, which is beyond what I'd like to cover in this particular talk. Since it's not the path that I've normally gone down with, I just want to make sure that you understand that even when you do go down this path of having a mono repo, it doesn't mean that you have to put everything inside the same stack as well. If you're talking about AWS and CloudFormation, you actually can't, because there's a 200 resources limit for a particular stack. The approach that I've normally used is having one repository per service, but we still need to identify those service boundaries. This is my quick mind map for the social network YABL, and you can very quickly identify a number of distinct features in this system. For example, we had a timeline feature, just like what you find in other social networks like Twitter and Facebook. But then there's also things like search, notifications, suggestion, chat, and so on. And all of these features in your system offers a good starting point for identifying your service boundaries. And you find that all these features, they evolve around a number of entities or concepts in your domain, such as users, relationships, brands, content, and so on. So all of these things can be used to identify your service boundaries, and each one of them can be managed by a single microservice and implemented using the most appropriate set of technologies. It could be containers, it could be running on serverless, and in terms of database and queues and streams. For example, if you're talking about relationships, to store the relationship data in a way that makes it easy for you to do complex queries like finding a second or third degree connections, or to find people in your network that has a shared interest, you probably want to consider putting the data and store them in a graph database such as Neo4j. And here, every service is going to get its own repository, and all the functions that have to work together as part of those microservices, they also belong in the same repository as well. And I typically set up one CI/CD pipeline for every single service, and therefore every repo, that will deploy all the functions as a single stack. So if there are other resources like DynamoDB tables that are only used and only make sense and relevant to that particular service, then we also include them as the same CloudFormation stack as well. And from there, we can use the Strangler pattern to incrementally move functionalities from our monolith to our new microservice architecture piece by piece. And search was our first target because it was an isolated feature, it was easy to implement, and I actually managed to implement and deploy the whole thing in just a couple of days. And we were able to use that to give us quick feedback on how our approach is working with this serverless, and that can help guide us towards how we migrate the rest of our system over. At the time, the search feature was essentially one big complex regex against MongoDB, which, as you can imagine, just didn't perform or scale to any satisfactory degree. In fact, we were struggling for performance with a very large MongoDB instance for about 100,000 users. And for a social network that aspires to have millions and millions of users globally, that's just clearly not good enough. And it was also very difficult for us to implement anything beyond rudimentary ranking on the search results. So since we have our monolith publishing all state changes to a Kinesis stream, so in terms of rewriting this search feature, I can just have a Lambda function that listens to user registrations whenever user follows one another or whenever they update their profile. For those events, I can react to them to update a user index in Amazon's cloud search, which is essentially a hosted version of Solr. And I was able to then build a new search API in front of that Solr cloud search using API Gateway and Lambda. And as part of our migration, instead of waiting for the mobile applications to then migrate to our new services, which then have to take even more time, we typically just update the monolith at the same time to then proxy the request to the search endpoints, in this case, the search endpoint, to our new service, so that we can deliver value to our customers right away. And when the mobile teams have the time in their backlog, they can then move to use the new search endpoints directly. At the time, we also decided to build a new analytics pipeline pretty soon after that. So for some reason, we were using mixpanel, and even though we are just starting out and we didn't have that much data to begin with, we signed a contract with mixpanel for the top tier, and which was about $3,000 per month. And our BI guy doesn't actually know how to work with their complicated, their JavaScript-based query language. And because mixpanel is designed for collecting generic, mobile usage events, people logging in, people signing out, moving from one screen to another, they don't actually understand our domain in that it's a social graph. Oftentimes, when we run a query, we want to find people that follow us, maybe Tiny Temper or another influencer. And we don't just want to target people that have signed in the last couple of days. We want to look at our social graph as well. So in this case, we were able to add another Lambda function that consumes all of the events that's being published by our legacy system. And we just live stream all of those events into Google BigQuery, which lets you run ad hoc queries against exabyte-sized data sets and still return results within seconds. And also, Google BigQuery, like many other services that we're going to talk about today, is all pay-per-use. So you only get charged for the data that BigQuery has to process, plus a minimal amount for storage. This whole pipeline took several iterations. The first iteration took just one developer 2 days to go from initial discussion to running something in production. And that was his first project with Serverless and Lambda as well. And our BI analyst who just joined us from Skype at the time came to us afterwards and said, Jesus, guys, nothing ever got done this fast at Skype, which is, of course, no offense to Skype, but it all goes back to the point of the lead time for someone being able to say thank you to the value that you've delivered is the metric that we should be optimized towards. And also, since cost wasn't our main driver for any of this work we're doing, it's actually really nice to find that based on the amount of data we actually had, we're able to do everything we use mixpanel for with BigQuery, and as you can see, there's like 10,000 x difference in terms of cost between using BigQuery for the workload we had to using mixpanels. So it's great to see we managed to deliver a lot of cost saving whilst also delivering more capabilities to our BI analysts as well. Of course, since then, Amazon also announced a new service called Athena. Well, not new anymore. It was announced in 2016 as a direct competition to BigQuery. And if I have to do this whole thing all over again, I will probably go with Athena. In which case, Kinesis is still my sink for all my events. And I can have a Kinesis file host, which then can collect and batch events from Kinesis and then dump them into S3, which is my data lake. And from there, I can run a crawler in the AWS Glue, which basically just runs periodically, look at the data you have in your S3 bucket, analyze the schema automatically to derive a table and catalog the data into tables that you can then query using Athena. So like BigQuery, you can run ad hoc queries against a very large set of data and still get answers back within seconds. And like BigQuery as well, Athena is also pay-per-use, so you only pay for data that you process with your query. And with Athena, you can then also hook up the results of your queries to QuickSight, which then allows you to create dashboards and visualization to very quickly see those query results. And also, QuickSight is also pay-per-use as well. And the nice thing about this whole thing is that I don't have to write any business logic myself. All it is just a few resources in AWS that I can provision with Terraform, with CloudFormation, whatever I decide to use. And all the things you see here, they're all pay-per-use as well, so that when I don't have data, when I'm not using it, I don't pay anything for them either. So I can capture user actions and report them into this nice BI dashboard with pretty much minimal effort, and it can all be done very, very quickly as well, just with a few resources I provision as part of my CI/CD pipeline. And as I mentioned, we had this timeline feature, which when I joined the company was already there, and it was running as part of the monolithic system, and in fact, it was one of the core features of the app. The problem was that it just didn't work, at least not in the way that it was designed. There was a detailed spec in terms of how, when you create a post, how you should get distributed to your followers and so on. And the QA team has put together a very good test case, very thorough test case. And for some reason, the implementation failed every single test. And the whole QA team declared the feature as untestable. And it was when we came in, we tried to understand what was actually going on. We also found that it was very much over-engineered. How over-engineered? Well, it was already using events to separate you posting a new content to distributing that content to your followers, which is a good thing. But the way it was doing it was with these modules that are named 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.js. And get this, they all do something slightly different, which of course you can't tell what they're doing by looking at the module name. And the naming actually matters because it dictates the order. And you've got this handler module thing that then requires all these other guys so that they are used to dictate what order in which things are processed. And I think it short circuits on the first processor, it finds that actually it's doing what it needs to do. As you can imagine, it's crazy trying to figure out what is actually going on here. And the people that actually put the system together, they couldn't debug it. And worst of all, the system didn't scale at all. Every post that you receive in your feed have to reconstruct your entire feed. And that's like saying, okay, to put on a glove on my hand, I have to construct a brand new hand with the glove attached to the new hand so that I can then reattach it to my body, which just sounds crazy. And of course, at that time, a new CTO has come in and fired the entire team that was involved with the old system. So for the better or worse, me and my friends, we came into the project, and we have no one that we can talk to figure out why it was done that way before. So instead of trying to reverse a broken system, we sat down with the product team to figure out what it was that they actually wanted to deliver. And we rebuilt the system from the ground up using, again, events, because the first thing we did, the whole migration, was to make sure our legacy system is publishing state changes into Kinesis streams. So in this case, we can then have Lambda functions that subscribe to various events, like I just posted something, and then based on that, figure out who my followers are, so where my post should be distributed to, push them into batches of about 100 or a couple hundred, I can't remember the exact number, and for each batch, publish a message into SNS, which then triggers another Lambda function to actually then take that post and add it to my followers' feed as a part of a ready sorted set. And the reason we proxy through SNS here is that between SNS and Lambda, you get retry out of the box. You get, I think, 3 retries, even when your function fails, and you also get delete queue support out of the box as well. And the reason why that's important for us is because we need to optimize for surviving the worst case scenario. What you find in all social networks is that, say, 90% of people on Twitter would have less than 100 followers, but then you have that 1% that's got 5, 10 million followers. So in the worst case scenario, when something fails, when one of those, when say Obama published a new post, you want to avoid repeating the expensive piece of work here, which is figuring out all of his followers and then try to distribute message to them. And once we have data in Redis, we can then create a new API in front of a Redis cluster with API gateway and Lambda. And as part of our usual migration strategy, we update the legacy system to proxy any requests to fetch your timeline and forward them to your new systems. In this case, we have a number of Lambda functions all working together as a cohesive unit that to provide this timeline feature we wanted. And so they all reside in the same repo, and they all deploy together, even though some of them, as part of our API, others are stream processing, listening to various different Kinesis events and different event sources. But it doesn't matter what event sources they're using. Ultimately, that is one cohesive unit that have to work together to deliver some feature. Another small but important detail to note here is that I try to keep this, when you're using the serverless framework, for a particular stack that you're describing various different functions, you can also give it a service name, which is then used to form the name of your function once it's deployed, because the serverless framework enforces a naming convention. So making sure that the API itself has got the same name as the service name just makes life a bit easier when I'm trying to figure out what functions are used as part of that microservice. And pretty much like every other social network you find on the planet, we also have a recommendation feature, which unfortunately also didn't work the way that you expect them to. And when I dig down to figure out what it's actually doing, it turns out it was just returning the first 30 users from a database by account creation time, which when I figured that out, it was just a case of what, why, how, why is this ever, why is it? Okay, so understandably, we decided to rebuild the recommendation feature again using Lambda and build on top of events. And since we have everything that's happening in the system all streamed to Google BigQuery, and that I can run complicated queries against Google BigQuery and still get answers back within a few seconds. So I can have a cron job that runs, say, once every hour, that make a query against Google BigQuery, where we apply some time decay formula so that when we're trying to figure out who's currently trending on a platform, if someone who's got many followers recently, that counts high towards their trendiness. And then once I run this query, I can figure out the trending users, put them in the DynamoDB table, and then put an API in front of that. At the same time, whenever you follow or unfollow anyone, those events are then subscribed by a Lambda function and used to update a social graph that we store as a graph database in Neo4j. In this case, we're using GrapheneDB, which just offers Neo4j as a hosted service. And then we're able to create a new suggestion API that can return you people that you might be interested in following based on your social graph. So this often includes your second or third degree connections. So people that follow the people that follows you, or the people that are followed by the people that you follow, and so on. And as part of our migration strategy, we will update the legacy endpoints to then, whenever someone asks for, give me suggestions for my people that you follow, instead of returning the first 30 people in the database in MongoDB, we will make a call to these two new APIs, amalgamate the results together, do some randomization, and then return you people that you may actually be interested in following. A nice little caveat to this whole thing was that it was mostly done in one night because I had trouble sleeping, and I thought, this feature doesn't work. We wanted to fix it for a long time, so let's get cracking. So with all the events that's already in place, I was able to get this thing rolling very, very quickly. And the last feature I want to talk about in terms of how do we do it was we also wanted to build a system for sending out push notifications to re-engage users that potentially have lapsed from the system. And that's actually one of the things that Mixpanel also gives you as well for that $3,000 a month we were paying. The downside is, as I mentioned before, it didn't understand the fact that we are a social network, we have a social graph, so that whilst it's easy for them for you to target anyone who signed in the last day or the last given some time period, you can't say, I want to send a push notification to anyone that follows Tiny Temper whenever he publishes a new post. So since we have everything that's happening in the system already recorded in Google BigQuery, and is a very, very powerful query engine that allows us to run very complicated queries, so it just makes sense for us to then build a system on top of that data we already have. In terms of the goal that we have for this new system we're building, it was a case of we wanted to be able to do ad hoc queries, which are often driven by the marketing team, who will say, okay, we're working with some influencer, they are doing a campaign, so whenever they publish a new post, we want to tell all their followers or people that follows music, for example, that, hey, Tiny Temper just joined the platform, maybe you want to come and follow them. At the same time, we also want to be able to do schedule notifications. This is often driven by the product team that want to say when someone started the sign-up process but didn't finish, so we try to give them a nudge to say, hey, please come back and finish signing up. Or once they have, say, haven't logged in for 21 days, give them a little push notification to say, please come back. Here are some interesting things that's happened that you may have missed. For this system, we also want to be able to do A/B testing to test the different messaging or different layout for the messages as well. So we want to be able to say, take some message you want to send out, have a control group where we don't send them anything, and then different variants that we're going to test different messagings that goes out to our users. And we also want this system to be scalable, to be capable of sending out millions of notifications as a system, as our network, our social network grows. And we, of course, we also want it to be cost effective. Again, it's not about spending less, it's about spending better. So for the schedule notifications, like we did before, we have a cron job, which is CloudWatch event that runs regularly based on the schedule, calls the Lambda function, which then runs a query against Google BigQuery to find anyone who started the sign-up process but didn't finish, and then construct the JSON payload, multiple JSON payloads, then puts them into S3, which can then trigger another Lambda function to then actually send out push notifications by talking to Google Cloud Messaging and Apple's messaging system, I forgot what it's called now. And since it's ultimately two separate subsystems, one to decide what to send, the other one to actually send out the push notification, it means that it was easy for us to extend this system to allow other subsystems to then be able to also send out push notifications as well. At this point, you might have a good question that, why did you talk to the platforms, the native messaging systems, and why not just use something like SNS? The reason for that was when the app was first launched, we didn't have integration with SNS. So to use SNS, we have to do quite a bit of work on the client. But also there's additional charges involved with sending out push notifications through SNS as well. So given the things that we already have, we decided that it was easy and cheaper to just use GCM and Apple's notification system directly. And for the ad hoc notifications, because they're driven by the marketing team, which have got their own metrics for success to drive engagement. So we had this dilemma of, okay, how much oversight do we put in place versus just letting them do what they want to do. The problem here is that the product team is very concerned about marketing team just spamming the user because they want to drive retention, they want to drive engagement and usage, but at the same time, we want to maintain that overall user experience. So the head of product is very concerned about just marketing teams spamming the user. It's a difficult balance to maintain, and eventually we decided on a workflow whereby the marketing team will work with analysts on what query they can use to target the right users, and then there's just a simple approval process that goes through the chief product officer as well as CTO, and as part of that process, the approver can see how many people is going to be targeted and also send out test notification to their own mobile so that they can see what it looks like before we actually decide to go ahead and send that push notification. In this case, I have created a very simple admin2, a simple UI as a single page application for the marketing team to use, which is served out of S3 as a single page application that integrates with Auth0 so that you go in there, you put down your BigQuery query and a few messages and notes for the approver, click a button, and then when you do that, it's going to hit API, which then stores your request in the DynamoDB, but at the same time also sends an email via Amazon's simple email service or SES to the approvers, which looks something like this, where you can see who requested it and how many people is going to be targeted. In this case, 45,000 people will receive this notification. And you have some notes, some message, the messaging. I don't have it here, but there's buttons to approve or reject the request, but also to say, please send me a test notification to see how this message actually renders on my phone. And once the approver decides to approve or reject the request, then again, his API gateway, Lambda, then updates the data for the request in DynamoDB, and then send out an email to confirm what's happened. And in the case of a request being approved, it then runs the query against Google BigQuery. Again, puts out this output, the same JSON payload, which we can use the thing we saw earlier to actually send out those push notifications to our users. So in this case, it's not one microservice, it's actually 3 separate microservices all working together. So that's just some of the examples that for things that we're able to do very, very quickly as we rebuild our system, but also building new features as well on top of events and also using serverless. There's also other things that we've done, which in this talk I'm not going to include in terms of how do you do monitoring, alerting, all of that. There's a talk I did for NDC London last year where I go into those things in more detail. So with that, I actually finished a bit earlier than I expected. So thank you guys very much for your time. If you've got any questions, I'm happy to take them now as well. Okay, yes, sure.
How do you handle latency involved in cold starts?
So the question is, how do you handle latency involved with cold starts? So with cold starts, I find that depending how long your cold start is, depends a lot on the number of factors around memory size that you're using for your function, because that determines how much CPU and bandwidth network bandwidth your function gets, and also depends an awful lot on what language you use. So I find that with Node.js, in production, I see anything between 300 to 500 milliseconds of cold start time. So that is well within what is acceptable for all of our APIs. So with cold start, you have to think about the frequency, how often you see it, which is not something that you can really control because it's all driven by traffic coming into your system. I can't tell the user when to use the API, so that when there's a spike, there's going to be a spike in terms of the number of cold starts I'm going to see. But what I can do is make sure that when those cold starts happen, the cold start duration is still within my acceptable response time. So that's what we do. We basically just make sure that for functions that are sitting on public user-facing APIs, that they are fast enough. Where that's not, we can't do that for various different reasons, then we just don't use serverless. And that's actually currently what we do for the zone as well, where we see a much bigger spike. I talk about how we have up to 1 million concurrent viewers on an event. And the funny thing about live events is that everybody logs in like 5 seconds before the match starts. So that spike is too steep, actually, for Lambda to handle. That's another thing to keep in mind in terms of concurrency is that even though with Lambda, you can say, I want a maximum concurrency to be, say, 50,000, so I can run 50,000 requests concurrently. What you can't change, at least it's a hard limit, is how fast you can go up to that from 0 to 5,000 concurrent executions. The limit is 500. So because the spike is too steep, so we actually can't use Lambda for the zone as part of our critical path, and we have to use containers where we can pre-scale the number of tasks we're running our ACS task. For everything else, Lambda, we're using Node.js, so the code size is actually not that bad. Cool. Any other questions? If not, I'm going to hang around here for a bit, so feel free to just come and grab me if you have any questions you have as well. Again, thank you guys very much for being here, for listening.